Well, my watch says it's 9 o'clock, so why don't we go ahead. First of all, good morning to everyone. Got quite a crowd here. My name is Dave Kassler, amateur radio, call sign KE0OG. And I was approached by the Duke City Hamfest people and asked to give a talk about SWR. So I went and looked up an old video that I did on it and pulled some charts from that. And I think that the best way to express this and to talk about it today is simply fun with SWR. We're going to look at some of the equations and what we can do with them and what you can do with them, and in the process maybe explain a little bit about the way antennas behave and so on. So you're free to ask questions anytime. You don't have to save them to the end unless they're really pesky, in which case you can save them till the end. So I have how many of you have seen my YouTube channel? Quite a few of you have. Okay, how many of you are Augies? That means subscribers. All right. That's great. YouTube has an interesting philosophy on figures of merit for video channels like that. And one of the ways they judge a channel is by the number of subscribers. That's kind of the primary way, which is odd because you can subscribe to a channel. What you're doing is giving YouTube your vote of confidence in a channel, and then not sign up for notifications from that channel and never hear from it again. So seems kind of strange. And they run anywhere around 5 to 15% or so of the people who subscribe to a channel actually sign up for notifications for new videos, which seems an odd number. But you know, YouTube is YouTube, and their only competitor is YouTube, and so they do what they want, and that's how they figure things. I do have about 56,000 subscribers. So I figure that if you look at the number of members in the ARRL versus the number of subscribers I've only penetrated halfway into the market. So got a little ways to go. This topic is by request of the folks here, SWR. This is part of their antenna track, and there's a lot of mythology around SWR. And I thought what we'd do, instead of trying to have some rigorous conversation about SWR, just have a little bit of fun with SWR and see where the underlying technical meaning of it takes us. Before we proceed, I'd like to thank, what's your name?
Bill.
Bill. Bill saved the day. I was told that the computer here would have OpenOffice and PowerPoint on it, and the computer only had PowerPoint. My charts are in OpenOffice. And so OpenOffice will read Microsoft PowerPoint charts, but Microsoft thumbs its nose at OpenOffice, so we couldn't do it on the other one. So thank you very much for being prepared and having your computer go get ready. So, all right, let's take a little bit at SWR. There's a lot of lore about SWR. Lore stands for community knowledge that's about half right and half wrong. And in SWR, there is this idea that if you can improve the SWR, you can improve your performance. In some cases, that is true. In other cases, it is not. There is the idea floating around that you can get a one-to-one SWR. Well, if you look at your standard dipole, what they don't tell you is if you put up a dipole according to the old formula, 468 over F in megahertz gives you the length of a half wavelength in feet. If you put up a dipole that size, you're going to have a central impedance that's anywhere from 30 to about 75 ohms, and it will have a reactive component. And we're going to see that here. What that means is if you put up your perfect dipole, which I did a couple weeks ago. I put up a 40-meter dipole. It was perfect in every way, except for the ways it didn't work. And I had wrapped the wire back around the end, and then I pulled real tight when I put it up to get it all the way up, and I'd unwrapped all that wire. But I could only get it down to a 1.6 SWR. And the reason for that is because of that reactive component in there. So we're going to take a little bit of a look at that and take some excursions. And I'm going to define SWR for you in the most basic possible way. It's the standing wave ratio. But let's just go through this lore. Lower SWR is better. First of all, what does SWR measure? Right. Usually we talk about antenna SWR, but what do we usually measure? We measure the antenna plus the feed line SWR, because we almost always measure SWR at the transmitter. So we're measuring the standing wave ratio, which is a figure of merit that tells us how much of the energy we send out is coming back. Okay? And that's really all it is. Now, if you have a dummy load, how much of your energy comes back? Nothing. Yeah, beautiful 1-to-1 SWR on your dummy load. Has anybody ever mounted a dummy load on a tower to get it up high? You know, I don't think so. The thing about the SWR, it's just simply a measure of the effectiveness of your transmission system, getting that energy out of your radio and up to the antenna. Now, back when we had vacuum tube radios, I'm looking around in here for somebody who isn't old enough to remember vacuum tube radios. Yeah. If you, Bill, did you have something you wanted to add? No, just waving your hand, okay. In the old vacuum tube radios, usually the output of that radio was something called a pi network. Do you remember that? Plate and load, okay. And that had a capacitor across the circuit, an inductor in series, and then a capacitor after that. And that was, if you look at that, that's mathematically equivalent to a capacitor in series, an inductor across the load, and a capacitor going out. You just play little games with some of the mathematics in there. So the pi circuit has become the T circuit, which is today's antenna tuner. Almost all of today's antenna tuners are made that way. So the old radios, which had who knows what for an output impedance, okay, we used that pi network to tune into whatever antenna you had. And nobody back then worried about SWR because it wasn't really important. I mean, it was there, but your pi network and your radio was going to load up your bed springs or whatever you would put out there for an antenna, and it did a really good job. And so we don't think of it as an antenna tuner built into the radio. We think of it as an output network for the transmitter, but it matched. You get it just right and your power goes through and it doesn't come back and you're in good shape. So what is happening is the new transistor radios came out. Transistors are current-driven devices, whereas tubes are voltage-driven devices. In a tube, you vary the voltage on the grid to vary the output. In a transistor, you vary the current going in to get the current out of the thing. They're current-driven devices. And the way you build a broadband amplifier, it's got to have a fixed impedance in order to work properly. And of course, what's the standard amateur impedance? 50 ohms, okay? Ever since World War II, when somebody invented 50 ohm coax, the world revolves around 50 ohms, except cable TV, which is 75. Have you ever noticed the price of RG6 cable down at Home Depot? It's about $0.10 a foot for 73 ohm cable. Now, RG8X I've never seen for $0.10 a foot. You can use the RG6, it is possible to do that. So what happened is it was important for the load to be 50 ohm resistive load so that all the power would transfer. If it doesn't transfer, what does it do? It comes back at you. Okay, and it's power. It's got to go somewhere. And it would be dissipated in the finals as heat, and you could blow finals. Some of the early Japanese radios with transistor finals were notorious. You had to make sure it matched or you'd blow it out. All modern radios have protective circuits. Now what they do is if you've got a bad match, they just refuse to work. You know, they just say, no, no thank you, I don't care what emergency you have, I'm not transmitting. So hence the introduction of the antenna tuner, okay? And now they're ubiquitous. Most rigs, most HF rigs these days, the 100-watt rigs come with a built-in tuner which will take a pretty good load and tune it up. But if you've got a really bad load, then you're going to need an external tuner. So what we're looking at here is the SWR only measures the amount of energy transferred from the radio to the antenna transmission line and antenna, assuming the SWR meter is at the transmitter. There are many other antenna parameters more important than SWR, like how well it performs, how high it is, radiation resistance, a bunch of things that aren't really easy to measure. But the reason SWR is such a big deal is it's so easy to measure, okay? And so that's what people do. So let's look at this right here. This is fun. It's a pretty short tether. Where there is an impedance mismatch. Now, impedance in RF is the ratio of the voltage to the current, right? Okay, and impedance is a technique, we'd call it resistance normally, but when we're dealing with reactance, we start having fun adding capacitive reactance, inductive reactance, and so on. So the impedance mismatch is the forward wave, the reflected wave. The forward wave is sometimes called the incident wave. If somebody is using that term, you can be sure they either are or are pretending to be a scientist. The incident wave and the reflected wave. And then this over here is the actual power coupled out. The reflection coefficient is a complex number. It means it has a J thingy in it, okay? It means it has both a resistive and a reactive part. And it's the absolute value of rho is between 0 and 1. I should have put absolute value on there. Okay, we only need the magnitude of that. The SWR is defined as 1 plus the reflection coefficient over 1 minus the reflection coefficient. And I'll do a couple samples of that. Now, while we're at it, we might as well look at a standard antenna. This is a simple antenna model with lumped coefficients. They're actually spread out across the length of the antenna, but we'll look at it. An antenna has radiation resistance. This is the conceptual resistance that you create a voltage across that with your current in the antenna, and that will give you the power that actually radiates, okay? The power that radiates comes from the radiation resistance. There's ohmic loss, just plain old heat in the conductor. there is some inductive reactance. What's a straight piece of wire? That's a one-turn coil, right? For those of you who've played with toroids. So there's always inductance. And then there's some capacitance in there too. You've heard of capacity hats on antennas? They create some capacitance for this right here. Now we know about inductive reactance and capacitive reactance. They have signs that are opposite each other. So if they cancel each other, you have zero reactance, just resistance. You have what's called a resonant circuit. Okay, so the definition of resonance, when the different types of reactants all cancel each other. Okay, oh, it's going to go, so good. This was my biggest worry about coming down here, is whether this chart would wiggle. This is actually from Wikipedia, and we're going to look at the blue wave here. The blue wave is the incident wave. Watch the wave going across over to here, okay? And then it's going to reflect. And we watch it reflect and come back this way over here. Well, what actually happens in a transmission line is you've got different waves going in different directions, but what you actually see is the single voltage that's the sum of the voltages going in different directions. And that's the black line. In this case, rho equals 1.0. Everything is reflected. Everything is reflected. And what you get is this standing wave. Now, the SWR is the maximum voltage of the combination wave divided by the minimum voltage of the combination wave. So the maximum voltage comes up here. We'll call that 2. We'll use peak to peak because it's a ratio, so we can use peak to peak, RMS, whatever we want. Comes up to here, comes down to 0, goes down, goes up here. So the maximum voltage of the combination wave is 2. The minimum voltage of the combination wave is 0. So the SWR is infinite. How many of you operate your stations this way? How many of you inadvertently operate your station? Okay. Let's look at something more realistic. This is a real station. In this case, rho is a half. Now, just taking these as voltage here, and I'm going to call it RMS so I can get these right here. Your forward going wave is the dark blue. See it going forward? Okay, and it goes across. And then the reflected wave is the red, and you can see it coming back here at the speed of light. By the way, the only way I could get this wave to slow down is we need to go nearly the speed of light too to catch up to it. So that's why everything seems to be coming so fast. So the percentage of power that is reflected, power, is 25%. Now, SWR is voltage. If you hear the term SWR, voltage SWR, it's redundant. SWR is voltage, okay? So the maximum voltage of the combination wave, look at the combination wave. It's got a max and a min, and a max and a min. The max voltage is 1.5. The minimum voltage is 0.5 for an SWR 3-to-1. Now, a 3-to-1 mismatch is something that a lot of the modern transceivers can touch up. Okay, so you're in the ballpark here. But now notice here at that so-called standing wave. Is it standing? No. The combination wave of the two has to move this way because it's transmitting power. Power is going from the transmitter to the antenna and being radiated. Some of it's being kicked back, but most of it is being radiated. Okay, so this so-called standing wave here isn't standing at all. The only time a standing wave stands is if you've got either a short or an open at the end of your transmission line. Okay, and oddly enough, transmission line that's open, the RF doesn't spill out the end like a hose, but actually gets reflected back because there's a complete impedance mismatch there. Okay, so this gives you an idea of what is going on. Now, I want you to take just a little bit of a notice here. Power is kind of this goes up as the square of the voltage. When this goes up here, that's real voltage, real wire, real ohmic losses, right? And the ohmic losses of something that goes between here and here and here and here is, because it goes up as the square, is going to be higher than the voltage loss just from the incident wave itself. And we'll come back to that a little bit and talk about how poor SWR helps turn perfectly good transmission lines into a heater. Okay, so now that we've done this, we've discovered that the fundamental definition is the maximum voltage of the combination wave divided by the minimum gives us our 3-to-1 standing wave ratio. Okay, doesn't this look like fun? Well, let's see, I have a degree in math and a degree in engineering, so yes, it does. I just want to look at a couple things here. The antenna model, the total impedance is the radiation resistance plus the ohmic resistance, and then we'll go over to the reactance axis, which is what the J means, and then you add the inductive reactance and subtract the capacitive reactance. Now, reactance is a function of the inductor and the frequency. So for a given inductance, as the frequency goes up, the reactance goes up. And you never knew it when you were introduced to pi in elementary school that it would keep appearing throughout your entire life. It does. This is the formula for capacitive reactance. As the frequency goes up, the capacitive reactance goes down. Now, by definition, resonance is when the capacitive and inductive reactances in the circuit cancel each other. You can set, if XL is equal to XC, you can set these two together, and you find that the frequency of resonance is 1 over 2 pi times the square root of the inductance in henries and the capacitance in farads. Okay, now, this is easy to get backwards. If you have a frequency less than the frequency of resonance, suppose an antenna is resonant at 7150 kilohertz, okay? For antennas at a lower, if you go to a lower frequency, okay, go to a lower frequency, so the antenna is now too long. If the antenna is too long, the capacitance will dominate. If you go to a frequency above the frequency of resonance, the inductance will dominate. So if an antenna is too short, it will behave as though it's capacitive. Well, what's real easy to do if we have an antenna that's too short, a vertical, say, for example, that's too short? What do we add? Add a loading coil, right? We're adding inductance to create the resonance. See where all this comes from? It all ties together neatly to those things. So I thought what we'd do is have a little fun here. This is where the fun part comes in. This is an antenna that is resonant on 7118 megahertz, okay? And I found two values of inductance, 50 microhenries and 10 picofarads, which will give 0 reactance in the circuit right there. But I want you to see something here. That happens at one frequency. Doesn't happen across a band or anything like that. It happens at one frequency. And so as you move away from it, you start picking up down here, let's see, inductive, I always get this backwards. You pick up reactance on the either side. And when you pick up reactance, you're going to have an impedance mismatch, so your SWR will change. All right, page down. There we go. Did I do 2? Yeah, I had 3 of them there. Okay. This one is 10 and 50. This one here, there's less reactance, so notice that that curve doesn't move as much. That might give you a hint that the SWR bandwidth might be broader, and one that moves even less. Okay, so if you've got a resonant frequency, the antenna is resistive with no reactance. At lower frequencies, the antenna is too short and has capacitive reactance, so you can add some inductance. At higher frequencies, the antenna is too long, you can put a capacity head on it or something like that. Now let's play with some real numbers here. Okay, for wire, really bare wire, in air. Air is the dielectric. You take 468, divide by the frequency in megahertz, get the distance in feet, given a 0.95 velocity factor in the wire. That means that radio waves, which move at the speed of light in whatever medium they're in, radio waves move through that copper, actually on the surface of the copper, at 0.95 of the speed of light. Now, if that sounds like we're slowing things down, we are. Some coax can get down as low as about 0.6 for a velocity factor. So the wire, we want to measure a half wavelength, because that makes us a dipole. And here's something interesting, dipole in free space. How many of you have your antennas in free space? You've been on the space shuttle, you've stuck an antenna out in free space. There's no such thing as free space. I do not know why people want to measure antennas or have any information at all about how an antenna does in free space. I do not have a tower that tall. So if you do the modeling and you put your ground however far away it really is, you will always find that the ground affects the radiation pattern of the antenna. Anyway, the impedance is 73 ohms plus J45. J45 ohms, which means that you've got an antenna that's got a reactive part and a resistive part. Now, it's a little bit more complicated than that, because that assumes an optimum height for the antenna. As you raise an antenna, the lobe, a dipole, raise a dipole, the radiation lobe tends to move down toward the horizon until you get to a half wavelength. When you go above a half wavelength, you start to bifurcate that pattern. You start getting resistance going up. By the time you get up to about 3/4 of a wavelength or so, you've got a nice double lobe pattern toward the horizon. So that's why I think the optimum height for an antenna which I have no way of achieving, is half wavelength high. I put up my 40-meter dipole I just built. I took 2 pieces of chain link fence top rail, and you can stick them in. They've got a narrowed section that sticks into the next one. And I can get 20 feet. Of course, I have to put some ropes up to keep it up in the air. But it's an easy way to get a 20-foot mast. And so I've got my dipole proudly up there at 20 feet, which means much of it's good NVIS antenna. Yeah.
What was the J? Is that the ground factor?
No, the J has to do with the reactance. Reactance and resistance do not add directly. They add at 90-degree angles. So, and I didn't bring any pictures of this, but if you figure that the horizontal axis starting at 0 is resistance, okay, going from 0 going out to infinity, and I think it's the capacitive, or I can never remember if it's capacitive or inductive, yeah.
Inductive goes up.
Inductive goes up, capacitance goes down, okay. It goes up at a right angle to it. So if you want to find the absolute value of it, you have to go out on the resistance, up on the inductance, and then you can measure that angle there. That's the phase angle. And then the absolute value of that is the impedance. Okay, so the impedance is the magnitude of that vector and the angle that's shown there. That's the easy way of explaining complex analysis. Being a mathematician, I like the complicated way of doing it. Okay, this is a diagram from Wikipedia. And we're going to spend some time with this diagram. This is, pick a frequency, any frequency. 7,150, okay, pick a frequency. At that frequency, and you've got a dipole that is a half electrical wavelength, okay? This picture shows the impedance, or the resistive impedance. Resistance is always positive, right? Resistive impedance going up way off the chart. This is a half wavelength right here. This is a full wavelength right here. This is 1.5 wavelengths right here. So if this were a 15-meter dipole, no, if you had a 7-meter dipole and tried to operate it on 15 meters, you'd be operating over here. How many of you remember the old days when you could use a 40-meter dipole on 15 meters? Yeah, quite a few of us do, and did. Nowadays, with the more sensitive transceivers, it's a little harder, because that's about 100 ohms right there, so you're going to need a tuner. So a half-wave dipole would be here, and it comes up in here. It's actually going to hit it right about there. And what I want to do is just look here at the quarter wavelength point and see what goes on when we're dealing with resonance. And we're going to discover something very interesting. We're going to discover that the lowest SWR is not necessarily the point of resonance of the antenna. Okay? You may have noticed that at one time or another. The lowest SWR is going to be where the blue line crosses the 0 line, because then you will have no reactive impedance. The question is, what is the resistance there? Because the resistance of a dipole, the center resistance, depends on how high off the ground the antenna is. Now, I have had people swear to me. They've practically sent armed guards to tell me that you can make a dipole on the ground and it will be exactly the right length when you raise it in the air. Now, I'm a polite guy, so I won't say that's baloney, but you can't. Yeah, the antenna impedance varies with height above ground. It varies with trees, rocks, whatever. Okay, what's the first rule in antenna engineering? Everything affects everything. Okay, so if you're going to put up a dipole, cut it a little long, fold the ends back on it, secure them tightly so you don't do what I did and unfold it as you tighten it up, but you will have the thing up and down a couple times while you try to get close. Now here's half a wavelength right here. Note, there's a little bit of reactance and the impedance is right there, okay? Now we're going to play some games with this. Let me go back. We're going to play some games. This is a very sharply moving curve, okay? Very sharply moving curve. This is moving really fast. What I want to do is look at antennas that are really close to half a wavelength. Like, for example, if this antenna were cut for 7150, I want to look from 7 megahertz up to 7.3 megahertz, okay? So that's just that much right there. Well, now, if we look at that and pretend that that line is a line, has a slope, and this line, the reactive line, has a line, okay, we can greatly simplify what's going on here to see kind of what happens to antennas when you move them close. So I drew a bunch of lines here. You can see this is 4/10 and so on. So we're just going to get in that one little spot right there, and you can ignore all of the fun things that are happening. But this is the point at half a wavelength where you're talking 73 ohm resistive, 42.5 ohm reactive at the half wavelength. And now you can see as I've come in on this, that's sort of a straight line near the frequency of resonance. So let's just play with that. And we come up with some equations to go with it. This is, I guess it was high school math. Not sure I remember back that far. Okay, so what we're going to do is play some games. The effect on feed point impedance of height above ground, okay, at half a wavelength is 70 ohms. If you go down, you're not usually over here. It's a half wavelength. You're usually down over here somewhere. 60 ohms, 50 ohms, 30 ohms. Okay, the height above ground for a 80 meter dipole for 0.2 or the 50 ohm point, that'd be 50 feet in the air for an 80 meter antenna, but only 27 feet in the air for 7 megahertz antenna. So I'm still a little low with my antenna. You know, it's down over here, so it's probably 40 ohm, something like that. Now, let's play games with SWR. We're using those equations, which I put in here, don't worry about them. The antenna's cut for 7.15 megahertz, so it's cut for the center of the 40 meter band. Now, I have picked some reactance values, okay, from the height, 73 ohms, and I've assumed some reactance values. Now, the reactance values cancel at resonance, okay? So they shouldn't matter, but they start to matter when you get away from the resonance. And what happens here, first of all, the lowest SWR is not at 7150, it's down over here at the bottom of the band. Anybody have a problem with that? Does that seem weird, counterintuitive, sort of un-amateur radio? Maybe this is some kind of a secret communist plot. SWR, again, measures just the ratio of the incident and reflected wave, okay? It's just measuring that sort of thing. And if you've got a bad SWR here too, partly because the impedance is so high, right? The impedance is not 50 ohms, it's 73. And then you've got a little bit of reactance in there too. So as you come this way, the impedance is such that between the reactive and resistive impedance, you can get down to about 1.4 to 1 SWR. If I see an SWR of 1 on an antenna I built, I know something's badly wrong. Okay, because real antennas don't go down to 1 SWR. So here again, we've got our 73 ohms. Now I've made the center frequency 7.3. My assumed reactance that I'm dealing with here is 42.5. Now, why would I have a reactance that high? At the resonant point, they'll cancel each other. That's over here. But the reason I have a reactance so high is that probably the antenna's too short, so I put in some inductive loading. Okay, so the antenna was capacitive, so I added some inductive loading. Okay, so at the frequency with lowest SWR, the world is wonderful, but as you go either side of it, you find the SWR going up and down pretty fast. Has anybody ever run into that problem? This is why an antenna like the MFJ Octopus will only tune on half the 40 meter band. You got to take it down and retune it for the other half the 40 meter band. It's because they add inductance to a too short antenna to get it to operate in the band, but the actual 2-to-1 bandwidth is not wide enough to cover the whole band. Usually on 40 and above, we like to have an antenna that's going to cover the entire band. With a dipole, that's easily possible. Now, why do I keep talking about 2-to-1? Your radio, if you've got a modern radio that has a tuner in it, like my Yaesu FTDX 3000 has a tuner, quote unquote, in it. It will touch up an antenna that's 3-to-1. It'll touch that up and add the right amount of reactance to bring that down. In fact, you can bring it all the way down to 1 by adding reactance. Let's talk about how antenna tuners work. An antenna tuner sits there and lets the signal go zipping through, and then here comes something back because the antenna has a complex impedance, okay? And so what the antenna tuner does is it puts the so-called complex conjugate impedance in there. What that means is if it's inductance there, it's capacitance here. Okay, and it catches that reflected wave in the reactive components, and next time around zaps it back at the antenna. Okay, and it keeps doing that. It gets that power and it sends it back toward the antenna. Sounds pretty good, doesn't it? Well, if you have a real antenna line that's not made of a superconductor, you're going to have a higher voltage on the line, and so you're going to get higher ohmic losses. You will heat the cable. Now, it depends on what kind of, here's a grand secret. Impedance is, let's see, equals I, so E over I is the impedance. 50 ohm impedance in coaxial cable. What does that mean? That means that the ratio of the voltage to the current is 50. If there's 1 amp of current, there's 50 volts. Okay, so if you've got 100 volts there, you'd have 2 amps. All right? Now, 600 ohms. What, ladder line? Okay, 600 ohms. That means the ratio of the voltage to the current is 600, not 50, 600. Now, what is it that creates ohmic losses? The current, right? The current creates the ohmic losses. If you go to a cable like twin lead, a window line is 450 ohms, that's 9 times the impedance. That means that you drop the current by a factor of 9. So if you're going to have a wave bouncing back and forth, do it in a high impedance line. You'll lose less in the copper. That's why they say use ladder line, something like that. There's nothing magic about ladder line. It just has a real high impedance, so the current's not very high, so you get less ohmic loss. So that's why we do that. Okay, here's an example now of a nice curve. It's still not quite 2 to 1 all the way across the band. Usually your amplifiers can handle 2 to 1. Here we're going up in impedance, and you see we get narrower bandwidth. Here is a case of 7.2, and I'm assuming a 50 ohm resistance because it's up high enough for that. Not terribly much capacitance. We're covering much more of the band. All right, so if you want wide bandwidth, you can't have loading coils and stuff like that in there because they will shorten the bandwidth. And here is one. Oh, yeah, that one's hardly doing well at all. The problem that we have here, we can find resonance, but we've got this weird resistance here that's causing us problems. The tuner would take that right out. But notice that's the best SWR that you can get. That's about the point where most transmitter circuits feed back. Here is 80 meters. Notice what happens here. A lot of you have these vertical antennas that say they cover 80 meters, when in fact you find out that they cover about 15 kilohertz of 80 meters. Okay, what's going on here is that there is reactance, and even though I put a low value in there for the reactance, the fact of the matter is the SWR just shoots all to heck when you get very far away from that center frequency. So you either need a way where you can actually vary the length of the antenna, like step-by-R does, or something like that where you can have a lower impedance. Otherwise, there is no antenna that really covers 80 well. The one exception is the thicker the wire on an antenna, the wider the bandwidth. So you can make an antenna that's like a cage, about that big around, and get a lot of coverage of 80 meters. Okay, let me cover this quickly. Let's suppose the SWR in an antenna is 3 to 1. This is at the antenna, between the transmission line and the antenna. So we have RG8X, 27 feet per dB times 3. Let's see, it's 81 feet away for 3 dB RG8X and 144. 50 watts of the transmitter. It's 50 volts. So you're losing 3 dB, so you get only 25 watts at the antenna. For 3 to 1 SWR, quarter of the power is reflected for 6.25 watts, so only 18.75 watts available for transmission. The reflected power is decremented by half coming back. You got 3 dB loss in the cable. Okay, so the transceiver, you see 50 watts out, 3.125 watts back. Okay, the SWR looks like 1.6. And you say, woohoo, I've got a great system. So it's actually a 3-to-1 SWR. Out of your 50 watts, you're only dissipating 18.75. This is the problem with coaxial cables, especially with high SWR. You lose power going out, and then when that reflected power comes back, you lose the same ratio of power, okay? So you transmit it back again and you heat the cable. I mean, the winter birds love your warm cables.
So Dave, that's the advantage of having a remote tuner then, if you're gonna.
Yes, yes.
Because you're shortening the area to heat.
Right. For example, a 43-foot vertical, okay? You usually put your tuner right at the base of that because a 43 vertical has a lousy SWR. But if you tune it right there, you're not going to lose the power. It just bounces back and forth and it radiates quite well. This is a chart that shows, yeah, I know I'm running a little late, sorry. If you start out right here, here is the loss dB in a transmission line. And as the SWR goes up at the antenna, you can see the losses in the cable climb dramatically as that SWR goes up. So poor SWR at the antenna can create losses, especially at VHF. There's at 14 megahertz. Final thoughts. SWR is easy to measure. Go home and measure yours today. Very easy to measure. Adding inductance to tune a short antenna will narrow its bandwidth, which we've seen here, okay? It's perfectly normal. Usually an SWR under 2-to-1 is okay, and under 3-to-1 can usually be handled by the built-in tuner, and high SWR will increase the cable losses. Okay. We're running a little bit late. Questions? Yeah. This will be, well, it'll be on my website, or on my YouTube channel, youtube.com/Dave Casler, DAVECASLER. Okay? Yeah.
What you mentioned with the diameter of the cable,
Yeah.
that affects the SWR also?
Yes. Yeah, right. Yeah, if you have a thicker wire, you'll get a very slightly higher bandwidth. Any others?
Yeah, well, which of your YouTube channels?
Oh, I just have one channel. That's Dave Casler.
A gazillion of different,
Well, I've got lots of different videos.
yeah, right. Which one will it be on?
It'll be coming up. I haven't put it up yet. It'll be up.
Oh, okay.
Yeah. We'll talk afterwards. I'll be out in the hallway. We've got to let the next people come in. Thank you. Thank you all very much for coming.